I'm Professor Hartman. So I want to go through a bunch of homework problems, or not homework problems, but example problems that I pulled out here from Chapter 6 in the textbook. So Chapter 6 covers energy. And energy, I think I mentioned this in one of my earlier videos, but it's worth stating again, is a scalar. It's not a vector. And in general, it makes solving problems in physics easier. Sometimes you have to use energy and momentum. We haven't covered momentum yet, but we will soon. Sometimes it can be just more just an energy-based approach, but in general, Newton's laws can be effectively reproduced using energy-based methods. And hopefully, as I kind of work through these problems, you'll see why they're easier than forces. So let's jump right into it. The first one here is this is chapter 6, number 4 from the book. And what it tells you is that there's a 1200 Newton crate resting on the floor, and they want to know how much work is required to move it at a constant speed of basically 5 meters along the floor against a frictional force of 230 newtons, and then 5 meters vertically, right? So let's do part A first, right? So basically, here's the picture, right? So this is the floor, right? And here's our crate. We know the weight of this thing is 1,200 newtons, right? Okay, so, well, I should be more precise. Let's say the weight is 1,200 newtons, like this. So it's going to be pointing down, right? So mg, right, equals 1,200 newtons. There's obviously a normal force sort of pointing up here, like this. Should be equal and opposite. I didn't really draw those the same length, but let's pretend they are. And there's some other force pushing it to the right, right? So we'll say this is just some applied force, right? F, like that. And we're moving some distance. Delta x, right, is 5 meters, like this. Okay, that's what we're going to move. Now you're told that we're moving at a constant speed, right? So here we're going to use something called the work energy theorem. Sorry, and there's friction pointing in the other direction. So let me actually do this because they say there's a frictional force. So let's do it this way. The force that's moving it to the right, we'll make that on this side. That's the applied force. And then the frictional force, I'll draw that in purple. And that'll be a little smaller. And that'll be kinetic friction, right? So it's like the lowercase fk. Okay. So we are going to use something called the work energy theorem. This is basically a statement of conservation of energy, work energy theorem. And what we're going to say here is that the total work, right, done on the system is equal to the change in the kinetic energy of the system. This is the work energy theorem. Now, the total work here, right, it is in two pieces, right? It's going to be the work done by the pushing force, right, plus the work done by friction. And then basically here, right, the change in kinetic energy is going to be 0. How do I know that? Well, basically I know this. I'll sort of just put this here. This is 0. Delta Ke is 0 since the velocity is constant. So since the velocity is not changing, neither is the kinetic energy. So we can basically say here the work done pushing this thing is equal to the negative of the work done by friction. So they want the force. Yes, the force. Okay. How much work? Sorry, that's what they want. The amount of work done. So, okay, let's look at the work due to friction, right? The work due to friction, right? Work in general is F delta x times the cosine of theta. So here this is going to be the frictional force times delta x times the cosine. Now the question is, what's the angle here? The angle is actually 180 degrees. Let me explain why that is. Well, let me call this theta for the time being, right? And this theta, this is the angle between F and delta x, between these two vectors. So let's just take a look at what's going on here. Delta x is in this direction, right? So if I sort of sketch this on a coordinate axis, right, it's like, well, let me just do it down here. So if I sketch this on a coordinate axis, right, my delta x is to the right, right? And friction, by definition, always opposes the motion, right? So my frictional force is to the left, like that, Fk. And so my angle is this angle here. We start here and we rotate like this. And so that angle theta is 180 degrees. And it turns out, well, the cosine of theta, sorry, the cosine of 180 is -1. So what we get is that the work of friction, right, is Fk delta x times the cosine of 180 degrees. Now this is in -1. This makes sense, right, because friction is always removing energy from the system. So it should be negative. So this is going to be minus Fk delta x. But Fk, right, the frictional force is actually the coefficient of friction. Well, actually, they give us the frictional force, so we actually don't need that. So that they give us this. They say Fk is, I think, 230 newtons, right? So this is going to be negative 230 newtons, right, times 5 meters. That's delta x, right? So 230 times 5. That's going to be negative 1150 joules. Sorry, not newtons. The units of energy are joules. So we'll put that in there as well. Joules. Okay, good. And so, therefore, right, the applied work, right, is negative the work of friction. So it's going to be negative 1150 joules. So that's positive. So the work done is equal and opposite, basically, right? And that's how you get to zero total work, and therefore no overall change in kinetic energy. Now for part B, they want to lift this thing vertically 5 meters, right? So here, this is the weight, right? So we have, mg pointing down like that. This is the ground. We have our normal force up like that. But the bottom line is that instead of delta x, we can kind of think of it as like delta y, right, is going to be 5 meters, like that. And they want the work done, right? So, sorry, they want the force done. Sorry, I know I'm bouncing back and forth here. How much work is required to move it at a constant speed? Okay, so there's two types of work here, right? As we go up, there's going to be a pulling force, right? So let's say we're off the floor now, right? So we're no longer on the floor. So I'll call this F lift, the lifting force, FL, for the lift, right? Because once we leave the floor, there's no longer a normal force because the ground can't exert a force on the bottom of the box. So again, right, the total work done is the change in the kinetic energy, but since we're moving at constant velocity again, change in kinetic energy is 0. So it's going to be basically the lift work, right, minus the gravitational work. I should say, well, let's say plus the gravitational work equals 0. So here, the work of the lift, right, is going to be negative the gravitational work. So this is going to be negative the gravitational force, which is mg, right, times delta y, again, times cosine of 180 degrees, because in this case, we're looking at the angle between delta y and mg would be this, right? That's also 180 degrees. So let's plug it in, right? We know that this is 1,200 newtons already, right? They tell us this is already 1,200 newtons. So the lifting, the amount of energy or work that is needed to lift this thing is going to be negative 1,200 newtons times 5 meters times -1 again, so it'll be a positive number, and that'll be 6,000 joules of work. Okay, so that's parts A and B for that question. Let's move on to this one, a little more complex. So here we have this piano, and it's sliding down this incline. And they give us sort of the pictures here, and they say, okay, this is it's kept from accelerating, right? So again, it's moving at a constant velocity again, right? That's sort of the basic idea, because they tell us it's kept from accelerating, right? So basically, what this tells us is that v is a constant, and that also tells us that delta Ke is 0 joules. By the just definition of kinetic energy. So the picture here is like this, right? I'm just going to sketch out sort of the free body diagram. This is just the inclined plane, right? And so we have let's see, work done by the piano. Yeah, so we're just doing it. We're just looking at the piano, right? So this dot will be the piano, right? And this is my y-axis. This will be my x-axis. Kind of go like that. Okay. And what we know, just to sort of draw things out, I know I did this before. That's mg, right? And that's sort of the weight. And then we're going to go ahead and do this, and that's the angle theta. That's the same angle as that. Basically, you can prove that. This piece here, right, that's mg cosine theta. And this piece here, which is going that way, is mg sine theta. This guy's pushing parallel, so he's pushing this way, along like that. We'll call that his force, F. And that's pretty much it, right? It's going down, so that's the deal. Okay, and we know what delta x is, and we know what our angle is. They want the force exerted by the man, so there are, so let's do this, right? So basically, all we care about is what's happening along the x-axis. So again, right, what we're going to say is basically, the total work equals change in KE, so therefore the total work is 0. The total work is the work. Now, we could call it whatever direction we want positive. Since we're moving to the right, I'll just call that positive. So we'll basically say, well, we'll say that the work, let's not do that just yet. So we'll say the work of the man plus the work of gravity, right? These are the two competing elements of work equals 0. The work of the man is going to be his force, delta x times the cosine of 180, right? Because he's having a negative effect. That's why it's the 180. Plus the force of gravity, which is mg, delta x times the cosine of 0, right? Because they're parallel. And that all equals 0. Okay, so basically now, right, this is -1, this is +1, and we can go ahead and plug these in. So we're going to get F delta x minus mg delta x equals 0. And so we can solve the delta x's will just cancel out because there's one sort of everywhere. So we can just solve now. Shockingly enough, right? This is mg. I left something out. Mg sine theta. Sine theta should be in there as well. Sine theta, because it's going this way. So okay. So this is sine. There's a sine theta here as well. And so if you go ahead and solve for the force, right, it's just mg sine theta, which is going to be, I think they give us the mass of the block, and the theta is 25 degrees. The piano is 380. So we know what's up here. So this is 380 kilograms times 9.8 meters per second squared times the sine of 25 degrees. And I'm going to put that in my calculator and see what I get. So that's 380 times 9.8 times the sine of 25. And I get about 1,574 newtons, let's say, approximately. Okay. Great. So that's part A. The work done on the piano by the man, right? So that's, now that we have the force, we can just do this, right? So for part B, we can just say that the work done by the man, right? That's F delta X. So that's going to be 1,574 newtons times delta X, which is, I'm going to say 2.9 meters. Yeah, 2.9 meters. And let's see what we get. So 1574 times 2.9, and that is 4564.6 joules of energy. Okay. Now let's move on to part C. The work done on the piano by the force of gravity. Well, that's much easier, right? So basically here, we can do this a couple different ways. It's moving, so gravity, right? Well, I guess we could just do it this way, right? The work done by gravity is going to be, you can kind of think of it, let's just do it this way, right? We're going to say mg sine theta delta x times the cosine of 180 degrees. And we know all these things, right? Now this we already know is 1574 because it's the same as the applied force, so that's 1574 newtons, right? Times delta x again, which is 2.9 meters, times cosine of 180, right? So basically it's going to be just the negative of this number, so negative 4564.6 joules. And then finally, the work done, the net work done on the piano, well, that's zero, right? Because we're moving at a constant velocity. So W net is 0 joules. So that's how you do that problem. A few more problems to do. I just have to sort of actually restart my computer. So I'm going to take a quick break and then come back and complete those other ones.